For today's lecture, we're going to talk a little bit about why we care about air quality, specifically here in Salt Lake City. We will talk about the linkages between weather, specifically cold air pools, and air quality. We'll introduce the Clean Air Act and a little bit of the history of the Clean Air Act, talk about terminology for air pollution, and specifically identify criteria air pollutants that are ones that are known to cause human health concerns and that are regulated by the U.S. government. So here we have an image of Salt Lake City during the winter. It's pretty familiar to anybody who's lived here for a while, and it always makes you wonder what the heck it is that you're breathing. This quote's a little bit dated, but it's still true today, that Salt Lake City is the 9th most toxic city in the United States, according to Forbes magazine. Similarly, the American Lung Association annually puts Salt Lake City in the top 5 most polluted cities in terms of short-term particle pollution. These are lists that you don't want to be at the top of, by the way. And then during the summertime, Salt Lake City ranks as the 36th most polluted city in terms of high ozone days, also from the American Lung Association report. I always love the mantra of the American Lung Association. They basically have a motto that if you can't breathe, nothing else matters. Think about that for a minute. It's very true. So let's talk a little bit about the relationship between weather, cold air pools, and air quality. So when we put pollutants into the atmosphere, they are moved around, of course, by the winds. It transports them. And depending upon the lifetime of the gas or particle, that will determine how far it will travel beyond its source region. So those winds are transporting it on those different scales. And during the transport, the gases and particles are undergoing chemical transformations. In terms of the particles, they can change composition, they can change size, and in terms of gases, they can undergo chemical reactions that actually convert them to particles through a process known as gas-to-particle conversion. The cold air pools, often referred to as inversions in the media, are really important for air quality here in Salt Lake City because they really prevent vertical mixing. And what the net effect of that is that the emissions that we put into the atmosphere down near the surface remain near the surface at a concentrated level. And this often leads to some of the most unhealthy air in the United States being observed right here in Salt Lake City. And how do you remove these pollution from these episodes? Well, you can either have really strong winds, which will advect it to different locations and scour out the valley, or you can have precipitation. Rain out and wash out can effectively remove particles and many gases from the atmosphere, and snowfall can do the same as well. So in terms of the transport, we've already said that the atmospheric lifetime determines how far it can be transported, and here I'm going to refer to the atmospheric lifetime as tau. And the lifetime of that pollutant is really controlled by its reactivity if it's a gas, by its size distribution if it's a particle, and by the meteorological conditions encountered during the transport. So for particles, if they encounter precipitation early on after they've been emitted, their atmospheric lifetime will be rather short. If, however, they are in an area of high pressure without any precipitation, they can persist for quite long periods of time. If you want to look in the notes section on the pages part of Canvas, I have a PDF which has the atmospheric lifetimes of many species in the atmosphere. So if a gas or particle has a lifetime of less than 1 day, it's primarily going to be a local pollution problem. If it has lifetimes between 1 day and 1 week, it's going to be a regional problem. If it has lifetimes greater than 1 week, it'll be spread to the continental scale. And if it has a lifetime of months to years, it'll be spread on a global scale. And in order to become well mixed in the atmosphere, it basically needs to have a lifetime of decades. So let's talk about vertical mixing. Well, you should be aware, of course, that vertical mixing is really controlled by the stability of the atmosphere and the depth of the boundary layer. If we have an unstable atmosphere, then vertical mixing is very easy. If we have a neutral atmosphere, then it's also fairly easy to mix. It won't happen spontaneously, but if there's any kind of forcing, it'll mix. And if we have a stable atmosphere, then the mixing is inhibited, and you'll end up with higher concentrations of pollutants. So for example, these cold air pools tend to create a stable atmosphere because we have a temperature inversion, and the boundary layer is typically very shallow. So here we have a situation where we have a deep boundary layer and no cold air pool, and we put in a certain amount of pollution, and it's diluted through mixing throughout the depth of the boundary layer. You can contrast that with a situation where we have a shallow boundary layer because we have a cold air pool. We have the same emission sources that are being put into this smaller volume. Because the dilution is less, the measured concentrations are higher, and the air, in fact, is more unhealthy in that situation. The boundary layer, however, varies with time of day, or it can vary significantly with time of day. The boundary layer tends to be shallowest during the night, and then as the sun rises and solar heating acts to warm the ground a little bit, it can increase the mixing, and you'll eventually end up entraining air from above the boundary layer into the boundary layer, which will then dilute whatever materials were inside the boundary layer until you reach a maximum in the afternoon, and then after sunset, the boundary layer collapses again. There are several different types of cold air pools that demonstrate different visual representations. The top left is a cloud-topped boundary layer. So this has liquid droplets, or often supercooled droplets, that are existing at the top of the boundary layer. At the bottom, we have a dry cold air pool. In this case, what you're looking at is the pollution and not the clouds themselves. And we can also have heterogeneous situations. This is most common when we have downslope flow out of the mountains, where we have clean air that's mixing into the valley. You can also have very, very heterogeneous pockets of pollution around the valley when you have that type of mixing as well. So let's talk a little bit about the Clean Air Act. So it's the law that basically gives the Environmental Protection Agency the power to regulate air quality. And the Clean Air Act was originally passed by President Nixon in 1970 and was significantly strengthened by George Bush in 1990. And Nixon created the Environmental Protection Agency in part to administer the Clean Air Act and the Clean Water Act. So what are some of the specifics of the Clean Air Act? Well, it authorizes the EPA to set limits for ambient concentrations of criteria air pollutants. These criteria air pollutants are the ones that we know can cause human health issues. And in addition to the criteria air pollutants, we also have hazardous air pollutants, which are known to be carcinogenic or mutagenic. And the EPA doesn't monitor the ambient concentrations of these species, but yet focuses in on setting limits on emissions and the tracking of these hazardous air pollutants. The one thing that the Clean Air Act is very clear about, pun intended, is that all of the regulations promulgated by the EPA have to be based on scientific evidence. You can't just say, we think that this species causes health effects. You have to have proof that goes through the scientific literature and through peer review. But once you have that scientific evidence, then it's the requirement of the EPA to basically track, monitor, and limit the exposure of the population in the United States to these hazardous pollutants and to the criteria air pollutants. Specifically, the criteria air pollutants that are regulated by the EPA are carbon monoxide, sulfur dioxide, nitrogen oxides, lead, which is a particle, ozone, PM10, which are particulate matter with aerodynamic diameters less than 10 micrometers, and then PM2.5, which are the fraction of the particles that have aerodynamic diameters less than 2.5 micrometers. These represent subsets of the total suspended particulate in the atmosphere, and these subsets are meant to kind of represent the specific particles that are able to enter into the nasal and the throat for PM10 and all the way down into the deep tissues of the lungs for PM2.5. So the EPA air quality enforcement, in order to enforce these air quality regulations, they have set up national ambient air quality standards, and they have to monitor the air quality in these regions to determine whether or not locations are in compliance or out of compliance. If they're out of compliance, then an area is designated as non-attainment zone, and the area has to come up with a state implementation plan within 1.5 to 3 years of the designation. And the idea of the state implementation plan is that it outlines a strategy by which they can get back into attainment. And how does the EPA enforce these? Well, if you fail to comply with these requirements and you don't make significant progress on your air quality issues, then you can lose access to all of the federal highway funds for a state. And this represents billions of dollars of infrastructure that every state wants to have. So that's really a strong incentive to meet the air quality standards. So how do we define air pollution? Well, the one that the EPA uses is that its pollution is the presence in the environment of any substance, no matter the source, that affects human health, well-being, or the well-being of other organisms exposed to the pollutant. So the key there is no matter the source. So there are anthropogenic, which are human-emitted pollutants, and there are naturally occurring pollutants as well. So if you think about naturally occurring pollutants, we have volcanic emissions, we have wildfires, we have blowing dust, we got sea salt, we've got biological materials, spores, pollen, and then there's also naturally occurring nitrogen and organic species and sulfur species that can be emitted to the atmosphere as well. We like to divide these up into what we call the primary and the secondary pollutants. Primary pollutants are ones that are emitted directly to the atmosphere. So you're behind a diesel bus at a stoplight, it hits the gas, it's fuel rich, and all of a sudden you see a big black cloud of soot that comes out. Those particles are primary emittents, primary pollutants. They're emitted directly to the atmosphere in that form. If you happen to be behind a car and it steps on the gas at the stoplight, you don't see anything coming out the tailpipe unless it's cold, and then you can see the water vapor condense that happens to be in the exhaust. But otherwise, you don't see anything. And you have these gases that come out, and some of those gases can then react in the atmosphere to create pollutants that do affect human health. Even though they're not emitted directly from the tailpipe, they result from the emissions of that tailpipe. And we refer to those as secondary pollutants. So what are the major atmospheric pollutants? In terms of gases, we've got our criteria air pollutants, sulfur dioxide, carbon monoxide, nitrogen oxides, ozone. But then I want to add to this list NH3, which is ammonia gas, and N2O, which is nitrous oxide. And then we have particles. Some of these are, once again, naturally occurring, and some of these are going to be anthropogenic. We have mineral dust, soot, and then we have the sulfur species, which can range from sulfuric acid gas to sulfuric acid liquid to sulfate, which is kind of a stabilized particulate form. And then we have nitric acid or nitrate, and then we have organic carbon. So let's talk a little bit about sulfur dioxide. It's a colorless gas. It's a primary pollutant. And the major anthropogenic sources are fossil fuel combustion, because sulfur is an impurity in these fossil fuels. And when you burn these fossil fuels, the sulfur that is in the fuel will react with oxygen at high temperatures to form sulfur dioxide. It's also a byproduct of smelting ores, because a lot of the processes that they use for mineral extraction require sulfuric acid, and that oxidizes at high temperatures to form sulfur dioxide. There are many natural sources of sulfur dioxide. Volcanic eruptions is a really large one, but we also have marine phytoplankton globally is a very significant source of dimethyl sulfide, which is then converted to sulfur dioxide in the atmosphere. We have carbon monoxide, and carbon monoxide is a major pollutant of urban air, and it's produced from incomplete combustion. The anthropogenic sources are basically poorly tuned engines. Cars that don't have a really good oxygen sensor, where you don't have the perfect mixture of fuel and air. When you have the combustion, can produce carbon monoxide. Cigarette smoke does the same thing, and wildfires do as well. Natural sources, the biggest natural source of carbon monoxide are wildfires. And carbon monoxide is really dangerous because the hemoglobin in your blood, which normally carries the oxygen, has a stronger affinity for carbon monoxide than it has for oxygen. So if your blood is given the choice between pulling out oxygen from the air or carbon monoxide from the air, it'll pull carbon monoxide and you'll end up suffocating. So limiting your exposure to carbon monoxide is a life or death situation. Nitrogen oxides. Remember that we referred to the criteria air pollutant as NOx, which is NOx, and that X refers to a 1 or a 2, so nitrogen oxide or nitrogen dioxide. We put them together collectively as NOx, and they're mainly formed from high temperature combustion. So remember we talked about the diatomic nitrogen N2 has a triple covalent bond, which is extremely strong. And the diatomic oxygen, O2, has a very strong double covalent bond. And it's very difficult to break those bonds. But at the high temperatures found inside combustion chambers, you can actually break apart the N2 and the O2 into molecular nitrogen and molecular oxygen. And then if they collide with one another, they can then form nitrogen oxide or nitrogen dioxide. So the anthropogenic sources, like I said, high temperature combustion, motor vehicles, biomass burning. Natural sources, primarily lightning is a very large natural source because of the high temperature associated with it, and also biomass burning or wildfires. Then we have ozone. Ozone, of course, is a secondary pollutant. It is not emitted directly into the atmosphere by any tailpipe emission. And also recall that ozone is both good and bad, the Jekyll-Hyde species. It's very good if it's located in the stratosphere because it blocks the harmful ultraviolet radiation by absorbing it. And it's very bad in the lower part of the atmosphere, in the troposphere where we live, because it is dangerous for your lungs. It's harmful to your lungs and it's harmful to plants. The sources of ozone, basically, as I said before, it's not directly emitted into the atmosphere, but it has to be cooked up. And the ingredients for cooking up ozone are volatile organic compounds. So what are VOCs? VOCs are organic vapors. They do have natural and anthropogenic sources. Most vegetation will give off VOCs at some point during their life cycle or during their daily cycle. If you want to smell a tree, if you can smell the tree, that's a VOC. And then we have nitrogen oxides, which can be natural or come from anthropogenic sources like cars or home heating or those sorts of things. And you combine VOCs and nitrogen oxides in the presence of sunlight, and you can generate ozone. And the chemical reactions that move this towards ozone are accelerated when the temperatures are high. And so ozone is generally a summertime phenomenon, with the exception of the Uinta Basin here in Utah, where it's the one place in the world that we know of that has significant concentrations of ozone during the wintertime. And that happens to be a unique situation associated with the extreme VOCs that are emitted from the oil and gas industry, the nitrogen oxides, which come from the combustion that's going on in the Uinta Valley and Uinta Basin. And then you have extreme sunlight when the ground is snow covered. You have UV radiation, which is coming down from above and being reflected off of the surface. And so it doubles the amount of UV radiation, which can then lead to ozone spikes in that region. And then we have particulate matter. The EPA doesn't regulate total suspended particulate mass anymore, but it is the total mass concentration, usually in micrograms per cubic meter, of particles that are in the air. PM10 is a subset of total suspended particulate. It's all those particles that have a diameter less than 10 micrometers. And then PM2.5 is a subset of PM10. And it is all the mass of the particles, the mass concentration of particles with aerodynamic diameters less than 2.5. And the units on these are usually micrograms per cubic meter. There are many different sources of particulate matter, and there are many natural sources of particulate matter as well. So which of these U.S. cities has the worst air pollution? Well, it really depends upon the type of pollution. So for example, Houston has some of the worst ozone problems in the United States. Los Angeles has some of the worst particulate pollution in the United States. And for many, many years, Salt Lake City had the worst sulfur dioxide concentration in the United States.